Welcome to the lecture on continuous cooling transformation diagrams. So, they are also known as the CCT diagrams popularly. Now, as we see in our earlier lecture, we discussed about the TTT diagram. In that we assumed that transformation is done at there is transformation at one temperature, that is isothermal transformation is there. Now, rarely you see that such is the case. So, rarely any steel is turned to a constant temperature and isothermally transformed, because temperature will change. So, it is normally continuously cooled from austenitizing temperature to room temperature at different cooling rates. So, certainly when you are cooling, then in that case you will have different cooling rates from the austenitizing temperature to the room temperature. So, if you have to take this also this continuous cooling case into account, in that case these CCT diagrams will be helpful, and CCT diagrams, they are depicting the transformation temperature and time relationship during continuous cooling, because there is normally a case of continuous cooling, and in that case you need to understand that how the transformation is going to proceed. So, specimen will be cooled from austenitic range at a constant cooling rate, and in that case you will have the paralytic start and finish points determined. So, basically again in this case you will have a constant cooling rate, and you will be in that you are having these points like when the perlite started and when the perlite was finished, and in that case, so the same thing will be done here also. You will have for a particular amount of time, and then in that case what you do is you will have further quenching. So, you can by knowing the fraction of suppose say martensite, because of the presence of austenite at any stage, you can understand it. So, so accordingly you will have the different points, and if you draw these locus of the points, then you will have these different curves that will be known as continuous cooling curves. So, if you draw the continuous cooling curve for the eutectoid steel, so that looks like this. So, as you see, in this case you will have the liquid steel steel heated to into this austenitic zone. This is eutectoid composition steel. So, then from here you are cooling at the different cooling rate. The cooling rate, this cooling rate is a slow cooling rate, whereas this cooling rate is known as, this is certainly the other curves are for the higher cooling rate than this. So, this is 3 degree per second. Similarly, this is 35 degree per second, 140 degree per second, and more than 140 degree per second. Now, what you see in this case, that you will have once you go for this cooling rate, you will have these points A and B which are formed, and what you see that this is basically paralytic start point A, and this point is the paralytic finish point B. So, they are using the metallographic method, and they are outlined. Now, they are at basically what you see is that they are at the lower temperature value x, and at a later time then as per shown by the TTT diagram, because the specimen has spent most of the time. So, that is cooling time at higher temperature. So, that is why there is a shift. So, you see that it is at A and it is at B, what you see as compared to that shown by the TTT diagram. Now, what you see that with these different cooling rates, you will have, so if you come to this, in this cooling rate case at this time. So, if you look at this probably 10 raised to the power 3 line comes here, something close to this. So, in this case at this point this transformation is completely complete for paralytic start and paralytic finish, and then so it will be complete transformation from austenite to perlite. If you are behind this, in that case you will have the different transformation. Now, in this case you will have now the different zones, that will be paralytic zones. So, you will have coarse perlite this side and then further fine perlite. Then in the lower side you will have the benite and all that. So, what happens that if you look at this microstructure, this graph, you see that a cooling rate of 3 degrees C per second. If you look at this line, that is your 3 degree per second. So, this will give you the fine perlite. So, your coming transformation is complete here. So, it will give you the finer perlite in this case. When you are going for very slow cooling. So, for very slow cooling of 0.01 degrees C. So, this is your very slow cooling rate. So, if you are coming with this cooling rate and in this case you are into this zone where the transformation is complete. So, this zone will give you the coarse paralytic structure. With 3 degrees C per second, this cooling rate, your transformation is complete here, and in this lower zone you will have the fine paralytic structure. Now, if you go for further the increase in the cooling rate. Now, if you go for the 35 degrees C per second. So, if this is the line which corresponds to the 35 degrees centigrade per second of cooling rate. So, it will be crossing this paralytic start. So, it is basically crossing this paralytic finish line. This is your paralytic finish and this is your paralytic start. This bold line. So, upper bold line is the paralytic start line and this lower bold line is the paralytic finish line. So, 35 degrees C per second, this is crossing that paralytic finish line near the nose. So, it is it is just crossing here and it will give you very fine paralytic structure. So, that is because of the very high higher cooling rate as compared to the earlier cases, and that is why whenever in normal case we talk that when if you have a higher cooling rate you will have finer structure. So, it is shown from here because this is the higher coarser perlite zone and this is the finer perlite zone. So, now if you look at this 140 degrees C, this is 140 degrees C per second of cooling rate is this, quite a high cooling rate. Now, this is just missing the paralytic curve. So, and it is also not entering the benitic zone. So, this is in the bottom side you have this side it is the benitic zone. So, this 140 degrees C per second line. So, this line is basically missing that paralytic start curve, and this will be transforming to all the martensite because there is no paralytic transformation, neither it is further going and being hold at this temperature and going into that isothermal transformation zone where the benite is formed, because in earlier case what we had seen that when you are coming this line, when you come past the nose of the C curve it is coming, and then when you are holding here then you are coming in this zone which is the benitic zone. Now, in this zone if you are having this 140 140 degree C per second line. So, and if you are continuing through it, so you will be getting the full martensitic structure in this case. So, you must have, so that basically defines the concept of the critical cooling rate. So, basically this critical cooling rate, this is the critical cooling rate because it is just touching the nose of the C curve outer part, and basically the cooling rate must be more than this, for the full hardening of the steel, for the full martensitic structure of the steel, your cooling rate must be exceeding this value. And if the steel, so in between 35 and 140, so if it is 140 and if it is more than 140, in that case you are getting the full hardening, the full transformation from austenite to martensite takes place. Whereas if you are between 35 and 140 degrees centigrade per second, then steel will be crossing that perlitic start, and it is not crossing that perlitic finish curve. So, what happens in this case, some of the austenite will be converted to perlite, not fully. So, that way what you see, and then you also, and then it will be part of austenite will be converted to perlite, and untransformed austenite will be passing through this Bennettich range. So, so this Bennettich curve will be, so for that this untransformed austenite will be passing through that Bennettich range of the TTD diagram, and Bennettich start curve basically for continuous cooling will be shifting somewhat to the right, so that very little austenite will be transforming to the benite. So, and rest will be transforming to martensite. So, that way if you analyze this curve, you can see that how with what cooling rate, what kind of transformation product is there. So, if you analyze, what you see is that if you have the cooling rate, so if you write the cooling rate, and for different cooling rate, if you so if cooling rate is taken as degree C per second, and if you take this transformation product, so for the cooling rate of less than 35 degree C per second, what you see that you have all perlitic structure. So, that is clear from here. If your cooling rate is less than this line, if the cooling rate is towards this, so in that case it is passing these perlitic start and perlitic finish line. So, your whole austenite is converted to perlite. Now, if it is between 35 to 140, so in that case you will have the perlite and martensite, and if you have more than 140, so in that case you are going to have all martensite structure. So, this is how these continuous cooling transformation curves can be understood for for the eutectoid type of steels. We can also understand with respect to the low alloy steels for nickel chromium moly steel. So, because in that case what we have seen that these nose of the curves, they shift towards right, and how how can you see that what will be the different type of what the different type of structure will be formed in that case. Now, so if you try to draw the continuous cooling curve for the nickel chrome moly steels. So, as we have seen earlier, we had seen that when you talk about these nickel chrome moly steel. So, if you take this axis as time and this is your temperature. Now, as you know that in this case you will have one line. So, now in this case what we see that this is your gamma plus martensite zone, and you will have a line that is for 8 degrees C per second. So, just you can see that with such a small cooling rate, also you are coming in the zone of martensite. Now, in this case, so this is gamma plus martensite here, not this. Now, after this, so your one zone is going like this. Now, what happens that if you look at the cooling rate, so this cooling rate goes like this. Now, the small cooling rate, which is suppose 0.006 degrees C per second. Now, for this cooling rate, what you see. Now, in this case, if you look at the continuous cooling curve, so it will and you have another line as 0.3 degrees C. So, this will be your 0.3 degrees C per second. So, for that small cooling rate, in between again you will have another line as the 0.02 degrees C per second. So, this is the different cooling rate. What you can see that you have very small values of this cooling rate, and in at least 8 degree you can see this is coming as the critical value. Now, in this case what you see that here you will have a line that that shows the different transformation lines. So, this line will be so this line, this zone will be alpha plus gamma. So, what we see in this continuous cooling curve line. Now, in this case you have, if you have cooling rate which is less than, so if cooling rate is less than 0.006 degree centigrade per second. Now, in that case your structure will be pro-eutectoid ferrite plus perlite. So, if it is so, in that case you will have this is the alpha plus gamma. So, that gamma, and this side you have, this is a perlite. So, you can see that you will have this alpha plus gamma, and then if your temperature cooling rate is even less than this, you are going to get alpha plus gamma and plus perlite. Now, if further when you go between 0.006 and 0.02 degrees C. So, if your cooling rate is maintained between these two temperatures, now in that case you will have a partial transformation of perlite. Now, you could have seen in your earlier cases. So, you started from 3 degrees C, if you look at this line. So, we started from 0.01 and we went up to even 3, and that was from 35 that we have seen that partial transformation, but otherwise there was complete transformation to perlite. But in this case your cooling rate even it is very small. So, that way what we see. So, in this case we see that when you have cooling rate between 0.006 to 0.02 degrees C, then you have partial transformation of perlite taking place, and in that case this untransformed austenite that will be transforming to, so that transforms to benite and martensite. So that transforms to benite and martensite at lower temperature. So that will be the case when your cooling rate is between 0.006 and between 0.02 degrees C. Now further, if you are increasing the cooling rate further, so now between 0. So you are further increasing to 0.02 to 0.3 degrees centigrade. So between 0.02 to 0.3 degrees C per second. Now if you look at this line, so in between there will be no perlite transformation. So so no perlite forms. So the final structure will be ferrite and benite and martensite, ferrite plus benite plus martensite, because this zone is basically the austenite plus benite. So you will have this gamma that will be transforming to the martensite. So that happens when your cooling rate is from 0.2 to 0.3 degrees C. Now when your cooling rate will be further changed, so cooling rate becomes 0.3 to 8 degrees C per second. So that was the extreme left curve. So this was the 8 degrees C per second. Now in this case what you see, the product is benite and martensite. So what you see that in this steel, in this nickel chromium moly steel, you are getting benetic structure, and when you are going for continuous cooling. So but when you have gone to eutectoid steel, if we have seen that in the case of eutectoid steel you are not getting that easily. So also what you see that the critical cooling rate which was there in the case of the eutectoid steel, it was 140 degrees C per second, but in this case the critical cooling rate is quite small, that is 8 degrees C per second. So your critical cooling rate that becomes to be 8 degrees C per second. So this is the difference what you see. This is because of the alloying elements, and this is about 20th part of or 18th part of the cooling rate what you see, what you have to maintain in the case of normal eutectoid steels. So so that's how the effect of alloying elements can be seen on the formation of phases, and how you can see with the help of these CCT curves that what cooling rate, what way. So what you see that if you put the if you add the alloying, that's why alloying alloyed steels have more hardenability. These alloying elements basically they are shifting towards the right, and continuous cooling, with that continuous cooling also which is in normal case without the use of alloying elements in the steel, it is very difficult to get the magnetic structure, whereas in this case in the case of continuous, because in the case of continuous cooling it is difficult to get the magnetic steel, you could have got in the case of TTT diagrams we look that you have to isothermally hold it and then you get that structure. But in this case the you are getting the magnetic structure, and also the critical cooling rate is reduced to half. It signifies that even at smaller cooling rate you are likely to have the magnetic and martensitic structures. So, that is an advantage of the use of alloying elements. So, in a nutshell, we should also know that what is the role of these alloying elements. You have alloying elements, there are different roles of these alloying elements, and their functions basically. So, if you talk about the function of alloying elements, now as you know that they are used. So, first of all, they are used as substitutional solutes. So, you have substitutional solutes in ferrite or austenite. So, many elements like you have the use of chromium or nickel or so. So, they are used as these elements which are used in ferrite or austenite, and they will be improving the properties like chromium and nickel. If you add into the ferrite or austenite, so they will be improving the corrosion resistance. So accordingly, so these this is the effect of these alloying elements. They will be strengthening the steel basically. So, once they go into that steel, so they will be strengthening the steel. Then they are also used as so their function will be like they will be working as non-metallic inclusions. So, non-metallic inclusions will be in different forms, like you have they can be oxides, sulfides, and silicates. So, oxides means you can have Al2O3 is there, so that becomes a non-metallic inclusion. You have MnS, so that is again another non-metallic inclusion, or MnSiO3, so magnesium silicate. So, that is another example of the silicate. So, these alloying elements will be working as the non-metallic inclusions. Then they can also be dissolved in cementite. So, dissolved in cementite, and they will be cementite, they will be dissolving as a part of the orthorhombic structure. So, as a part of orthorhombic structure. So, you have also like FeMn3C. So, that way it is found. Then one of the very important use of these alloying elements will be that they are present as carbides. So, like they are having fine alloy carbides and nitrides also. So, like normally you have alloying elements which are more carbide forming or nitride forming elements. So, you have niobium, so that makes niobium carbide. You have vanadium, so vanadium nitride. Tungsten is used, tungsten makes tungsten carbide. So, that way these alloying elements are normally the carbide or the nitride forming elements. So, and also like chromium is making Cr23C6. So, that way these are normally the carbide or nitride forming elements, and they provide the strength. And then you have also insoluble metals like copper and lead. So, insoluble metals. So, you have like copper and lead. So, this way you have different types of alloying elements, and their roles are different, as we have understood. One of the function when we talk about these CCT or TTT curves. So, in that the very important point is that they normally try to increase the hardenability of the steel. Increasing the hardenability of the steel means that basically there is shift of the nose of the C curve towards the right. So, if the shift is towards the right, in that case you can have full hardening, you can have the martensitic structure, or you can have better structure with better properties even at a smaller cooling rate. Otherwise, you may have to go for a very large cooling rate for getting the fully martensitic structure. So, that is the chief advantage of using these alloying elements. Apart from that, many a times some of the sulfides or phosphides or insoluble metals, they are basically for improving the machinability of the steel, and many a times these alloy carbides, they will be pinning down the migrating boundaries, and they will be also that is basically during the recrystallization and grain growth. So, they will be helping in getting a fine size. So, that is another advantage of these alloying elements. And then more importantly, again these carbides or nitrides or some carbides like molybdenum carbide or vanadium carbide. So, they are enhancing the creep strength. Some of the carbides they also increase the wear resistance or abrasion resistance. So, these are typically the effect of these alloying elements, and their also effect also is there towards the hardenability of the steel, from where we can get the full hardening of the steel, we can get the martensitic structure or so. So, this is all about the continuous cooling transformation curves, and some summary about also the use of alloying elements and their functions in a right spirit in the steels. Thank you very much.